Yes.
Yes, all right. So we each have our own idea of what good signal means. And as Renzo just described it very nicely, we've each operationalized this idea in our own way. But one person's good signal might very well be another person's bad signal. And it really does depend on the application. As Camille's going to describe after me, the only bad signal is the signal you don't understand. And so my job for the next few minutes is to talk about a few of the things that I do in order to characterize my data and decide which acquisition is the right one for a particular experiment. I'm saying nothing about this advertisement for the Slack channel we all use, but up in the upper right corner of my slide is going to be the URL if you haven't yet joined that Slack channel. All right, so I've always studied vision, which means that it's very likely on any given experiment I'm acquiring coronal slices in posterior cortex using some kind of an open-faced surface coil. For a long time, all of my high-res work was either spin echo or GRACE, because I greatly fear large veins, and when I see these high beta weight regions in my image, my first thought is that is the signal that I don't want. But gradient echo EPI does have a lot of advantages when it comes to the trade-offs that we need to make between coverage and acquisition speed and power deposition and contrast to noise ratio. So here's a coordinate system that I'm going to use to frame this idea of good signal. One thing you do care about is coverage, but not always. Sometimes you just need to see one little tiny brain region. Sometimes you need multiple brain areas. And better coverage does help with good registration between functional and anatomical data. So that's one dimension. Another thing we're all trying to do is minimize our image blurring. And then of course, we would always love high contrast to noise ratio, although really low CNR just means you're going to spend longer in the scanner. So I think we're all reaching for this front corner of the space, but we also know we can't be there. And so what I'm talking about is the sacrifices and the decisions we make about which dimension we're going to sacrifice on. So I'm going to frame these comments in the context of a recent experiment where I was trying to decide whether to use a 3D GRACE or a 2D spin echo or a 2D gradient echo acquisition. I'll only talk about coverage briefly because it depends so much on the coil you're using and the particular pulse sequence implementation that you have. The numbers I have here, they are not cutting edge, but they're reasonable. And the bottom line always ends up that it's hard to beat gradient echo EPI when it comes to easy coverage. The limiting factors that I'm writing across the bottom of this slide, I'm serious when I talk about acoustic noise. I currently am running several protocols for like general populations that my coverage is limited, or my TR is limited by my willingness to expose participants to loud noise. Cutting the duty cycle can have a meaningful impact on the A-weighted sound pressure level in the scanner. I think it matters, and I think we should be measuring it. And so for the particular application I was doing, I didn't need more than 36 slices to cover the region of interest I cared about, so I left them out just to make the acoustics more tolerable for my participants. The next dimension is contrast to noise ratio, also terribly difficult to talk about in general terms because precise details are so dependent on task and region of interest and the individual subject. The contrast to noise ratio is the detectability of the functional signal changes that we're trying to measure. It's dependent in part on the signal to noise ratio and the temporal signal to noise ratio. For example, your mean in a voxel divided by the standard deviation is relatively easy to estimate. But the contrast to noise ratio is kind of hard to operationalize. So what I do is I take a task that I know, here's a PRF mapping task, and I run it in the same subject in the same region of interest with the different pulse sequences that I'm comparing. And then I'm calculating the fraction of the voxels in primary visual cortex that were modulated at a P less than 0.01 level. And so if you plot that against the signal to noise ratio, they're related. But then these T2 star weighted techniques, they just have such an advantage when it comes to driving voxels. And plots like this kind of explain why we keep using gradient echo EPI, even though we know it has a problem with those big veins. The thing I'm most excited about lately is figuring out ways to talk about image blurring. A lot of us work at 0.8 millimeter nominal resolution. It's this hardware sweet spot. Also gives us 3 samples through the cortical depth when we're doing layer-fMRI. That's the nominal resolution. What's the true resolution? There's a lot of ways of answering that question. They fall into kind of 2 categories. the image resolution or the degradation of the image resolution is caused by acquisition factors like signal decay or displacement during the readout, or how you handle the reconstruction of your partial K-space. I'll talk about this as image resolution. That's what I'm focusing on. There's also the effective or the functional resolution, which depends greatly on which contrast mechanism you've chosen and incorporates also concerns about the physiological sources of blurring. I'm not really going to touch on that. I'm pretty sure that Camille is going to talk about that in a second. The way I've been characterizing my image resolution is to use Affin's functions for estimating the structure of the spatial autocorrelations in my residual noise in my functional experiment. If you look at the residuals after you run your GLM, you've detrended and demeaned your data, and you've hopefully stripped out the correlations that are introduced by your stimulus response. And then Affin's functions are going to estimate your noise correlation structure as a weighted sum of a Gaussian term, which is going to represent probably your thermal noise, and an exponential decay, this long-tailed physiological noise that has been greatly discussed in low-res experiments lately. As this map shows, in this 0.8 millimeter regime we work, we are pretty much thermal noise dominated. And even in my gray matter, 95% of my noise can be described by a Gaussian kernel. If you look at maps of the width of that Gaussian kernel, you'll see this banding across in my phase encode direction. This was a right-left phase encode acquisition. Phase encode is always the toughest direction when we're working with EPI. And so what I'm going to do is I'm going to drill down into separately estimating the width of that Gaussian kernel in the X, Y, and Z dimensions. When you're 95% Gaussian, you can use this classic Affini ACF function. And what I'm plotting is estimates of the width of the Gaussian kernel that describes the spatial autocorrelations of my noise in my data as acquired, and then as it's been motion and distortion compensated. So I keep track of that as I start comparing pulse sequences and processing techniques. And in a 2D acquisition, your slice direction is always really well behaved and pretty close to the theoretical minimum, your nominal resolution. And then this particular gradient echo acquisition, it was a partial Fourier K-space acquisition that got zero filled. And so it had a really inflated blurring in the phase encode direction. There's also blurring that's due just to T2 star decay during readout, or distortion from field imperfections. But these are the parameters that I'm starting to really pay attention to as I characterize my data to know what really the practical resolution of my image acquisition is. This third parameter, I'm not talking about it today, but it's kind of an eye-popping map. This is the distribution of the C parameter, which describes the long tail of the probably physiological noise correlations in my data. And the way it just nicely maps onto gray matter and white matter reinforces the idea that it's physiological. And then I'll see these voxels that have hugely long spatial correlations that look suspiciously like the locations of large vessels. So I'll wrap now with a return to this coordinate system for the protocol I was developing. I ended up picking gradient echo because I wanted a lot of voxels to work with and easy coverage, and I was willing to sacrifice some spatial specificity. Having picked gradient echo, that leaves me with the problem of figuring out what to do about big veins. And if I'm not mistaken, that is what our next speaker is going to talk about. So I will stop sharing and let Camille take over.